First, let's define a matching network. Suppose a transmission line having a characteristic impedance of Z0 is being used to drive a load with input impedance ZL, as seen here. We know that if ZL is not equal to Z0, this will result in some fraction of the voltage signal being reflected back up the feed line according to gamma L, which is given by ZL minus Z0 over ZL plus Z0. If our goal is to maximize the power transfer to the load, we need to minimize the power being reflected back up the line. In other words, we need to minimize gamma L. We can do this by adding an extra bit of circuitry here, between the load and the line, which is carefully designed so that the new input impedance to this new load is equal to Z0, the characteristic impedance of the line. This matching network, attached to the load, forces the input reflection coefficient to 0, preventing voltage reflection and maximizing the power transfer to the load. So let's look at the design of this matching network for a moment. One very simple sort of network that can be used to achieve a match is called a quarter wave transformer, where we just add a quarter wave length of transmission line with characteristic impedance Z1. We know that the input impedance to a length of transmission line terminated with a load is given by this equation, where Z1 is the characteristic impedance of the line, L is the length of the line, ZL is the load impedance, and beta is 2 pi over lambda. Since we're adding a quarter wave length of line, L is lambda over 4. So the argument of the tangent functions is pi over 2. The tangent function approaches infinity at pi over 2. So the input impedance Zn is going to go to Z1 squared over ZL. Now, the reflection coefficient seen at the input to the network is given by Zn minus Z0 over Zn plus Z0. Our goal here is to eliminate that reflection. So let's set that gamma equal to 0. This equation can then be solved to find the appropriate characteristic impedance for the quarter wave line, which turns out to be given by the square root of Z0 times ZL. So to summarize, a quarter wave transformer is a length of transmission line with length equal to lambda over 4 and characteristic impedance equal to the geometric mean of the load impedance and the system impedance. Adding a quarter wave transformer between the load and the feed line transforms the input impedance so that it matches the feed line in order to minimize reflection and maximize power transfer to the load. This matching method has two fundamental limitations. The first is that the length of the added line segment must be lambda over 4, which can only be true at a single frequency. This means that the quarter wave transformer network is not appropriate to achieve broadband matching. The second is that a quarter wave transformer can only be used to match purely real loads. A lossless transmission line, like the quarter wave section we've added here, has a purely real characteristic impedance. So if you have a complex load impedance, the calculated Z1 value will be unachievable. To match a complex load, we will need to explore other matching network options. But more complex structures quickly become much more difficult to design via pure mathematical manipulation. Luckily, there's a graphical tool that can be used to greatly simplify this design process, the Smith chart. We're going to take some time to consider this powerful design tool.